Welcome to aminacademy.com. In fluid mechanics, let us discuss about Venturimeter. Look at this figure. Here, this is the Venturimeter. Now, we are considering the inlet section 1 and the throat section 2. Here, inlet section 1 and throat section 2. D1 is diameter at inlet. D2 is diameter at throat. V1 is velocity of the fluid at 1. Here V2 equal velocity at throat. A is area of section 1, area at section 1, A1 area at section 1, A2 equal area at section 2 of throat. Now here, because of the how it's working, because the flow of fluid is flowing through D1, which is a higher diameter, and flow through in velocity V1, and it contracts through the lower diameter, that is in throat. Due to this area of contraction, that means the velocity increases. Due to that increases, this partial vacuum is created, so its pressure is reduced, and here the pressure is increased. Now here the pressure difference is H plus delta H minus delta H is H here. Here is the D2. Now by using Bernoulli's equation, by using Bernoulli's equation for flow, P1 by rho g plus V1 squared by 2g plus Z1 equal P2 by rho g plus V2 squared by 2g plus Z2. Here the pipe is level, we have to get it Z1 equal to Z2. Level of inlet and throat is same level, so we can cut both. Then we can write P1 by rho g plus V1 squared by 2g equal P2 by rho g plus V2 squared by 2g. From that we can write P1 minus P2 by rho g equal V2 squared by 2g minus V1 squared by 2g. Let here P1 minus P2 by rho g, that is a pressure head converted as H. P1 minus P2 by rho g equal H we are keeping. Now we can write H equal V2 squared by 2g minus V1 squared by 2g. By flow equation, applying continuity equation at section 1 and throat 2, that is A1 V1 cross sectional area and velocity multiplied equal A2 V2 at throat. Now from this V1 equal A2 V2 by A1. Now substitute in equation 1 that we have, then we will substitute this one. We have H equal V2 V2 square by 2G minus V1. Instead of V1 we can substitute this, therefore V1 squared is A2 V2 by A1 the square by 2G. So therefore H we can get it V2 squared by 2G common 1 minus V2 squared by 2G common, we can get it 1 minus A2 square minus A1 square, which is equal further V2 squared by 2G A1 squared minus A2 square by A1 square. Now therefore we can write from this, that is H is equal this, therefore we can write V2 equal square root of 2GH and square root of that A2 A1 cross multiplied here, A1 square is square root is A1 over square root of A1 squared minus A2 square. Now discharge through meter, discharge through Venturimeter is Q, is formula is A2 V2. A2 V2 or A1 V1, we are keeping A2 V2, therefore Q, discharge Q equal A2 and V2, instead of V2 you can substitute root of 2GH into A1 by square root of A1 squared minus A2 squared. So therefore Q we can write A1 A2 by square root of A1 squared minus A2 squared into square root of 2GH. This is the discharge under ideal condition and is called theoretical discharge. Therefore, we can say it is theoretical discharge through Venturimeter is Q equal A1 A2 over A1 squared minus A2 square into square root of 2GH. Now from this but actual discharge will be less than theoretical discharge because of the friction between the fluid and glass tubes or tube material of the Venturimeter will affect the flow condition. That is, it's called practical discharge. We have to, that is practical or actual, we can tell actual. Instead of practical you can write actual discharge is, we can write Q actual. We have to introduce coefficient of discharge. Coefficient of discharge is CD into A1 A2 over A1 squared minus A2 squared into square root of 2GH. This is the actual discharge, where here CD called coefficient of discharge. Now, so next condition is value of H given by differential U-tube manometer, differential U-tube manometer. Look at this figure here. The Venturimeter is fixed with differential manometer. The reading is given by this Venturimeter differential manometer. By using this H, we can find the flow through Venturimeter. That is, let that case 1 here do. Case 1 is the differential manometer contains liquid which is heavier than liquid flowing through the pipe. That is, liquid in manometer is heavier than liquid in pipe, liquid or fluid in pipe. In that case, let HH is specific gravity of heavier liquid. Then SP is specific gravity of flowing through pipe, gravity of liquid flowing through pipe. Then X equal difference of heavier liquid column. Difference of heavier liquid column. That means here, look at this figure. Here differential manometer is fixed here. Suppose this H, consider this is a X. Now, therefore, H is expressed X into SH over SP minus 1. Here we are keeping this not H, only this keeping this X. That X is expressed in terms of S is SH means specific gravity of heavier liquid over specific gravity of passing through pipe minus 1. This is the, we are having H here. Case 2, if the differential manometer here, liquid in manometer is having lighter lighter density than liquid flowing through pipe flowing in pipe. That means we have to consider this liquid which is flowing is this heavier than this liquid, so it comes in inverted. That means this U tube comes in upper position. Like for that case we consider like same H is expressed x into 1 minus SH minus SP, because here heavier liquid is which is passing through the pipe. Now case 3, inclined venturimeter. Inclined means with differential U tube manometer. Inclined venturimeter with differential manometer. That means with inclined venturimeter is fixed with a differential manometer. Then for this condition we can get it. H is expressed P1 by rho g plus Z1, because here datum is changing because it's inclination. Then P2 by rho g plus Z2 equal x into SH over SP minus 1. Now case 4, similarly for inclined venturimeter in which the differential manometer contains a liquid which is lighter. Here liquid in manometer is lighter density than in pipe. T then which is flowing in pipe equal same H is expressed P1 by rho g plus Z1 minus P2 by rho g plus Z2 equal x into 1 minus SH minus SP. So we have done. Please subscribe our YouTube channel.